So hello everyone. After a long while we are back to the channel, and today we're gonna solve one of the problems in NEET 2025, that is, people are saying, which is beyond JEE advanced level, this and that. So you have probably seen multiple approaches for this problem. Today I will show you a very time friendly approach. Probably this is very new for you, but just let me take you through it. So to start with, I will give you some theory. The solution to the problem is very short, but knowing the theory is important. So if any one of you will end up in mechanical engineering, you will probably study this in third semester. So we have a relation between. There are two types of force on the fluid. On any fluid, a fluid like this is given in the question, and one of those forces are body force. Okay, so and body force is what? Generally the things like pressure and those things are considered inside body force. So if X is body force on on a unit mass of the body, so rho times X, where rho is the density of the fluid, is equal to the gradient of pressure in the fluid. Okay, so I hope you know what gradient is. So unless you don't know, then gradient of P, this is nothing but this thing, and I hope you know this, because if you are preparing for JEE, you probably know this, but still I am giving you the definition. Okay, so this is the gradient. Okay, it basically converts a scalar quantity, which is pressure here, so it converts it into a vector field. Okay, just a minute, wait a minute. Yeah. Now this is the definition of gradient operator. So okay, so now let us get to the problem. Okay, so we have been given a jar like this. So let me, this is the fluid here, and the surface is like this. Okay, so let me consider a small element like here, and here the pressure will be like this. It will be nothing but rho gy, and there will be a surface tension S, and the surface tension you can divide it in two components. This is theta, and this is the vertical component of surface tension, Sx, and this is the horizontal of surface tension, Sy. Okay, so now the trick in this question was to write, this is my approach. You can also have solved by the force balance method, which is a little long. So what you can write for this surface, you can see this surface, the surface of the fluid. Okay, so at this surface, what the quantity will hold, that dP is equal to 0. Okay, what I mean is that at the surface, whatever height that it is, whatever the surface is, the pressure is throughout the same on the surface. Okay, on the surface of the fluid. And what you can write dP as? dP you can be written as del P del X. I hope you know this too, but if you do not know, please know that any quantity can be written in partial derivatives like this. There would have been a Z term if there was any variation in Z, but here we do not have Z. So anyway, so this is given, and in this question dP is 0. So which means del P del X, this term is 0. So now what are del P del X and del P del Y? So del P del X and del P del Y are nothing but, let me write. So del P del X is nothing, before that, let me give you an important equation which all of you probably know. Here, the pressure difference between the outer and inner side of the surface, this would be nothing but delta P is equal to S by R, where S is the given surface tension and R is the radius of curvature at that point. Okay, at any point you can take throughout this surface. We have a long surface from X is from 0 to L, and you can take the radius of curvature at any point. Okay, so this is delta P is equal to S by R. I hope all of you know this equation. This is nothing but our expression for excess pressure. So this is such, and now let us do a thing. Okay, we will approximate. I mean, you can do this in general ways. Del P del X. This we will approximate by delta P divided by delta X, and delta P is this thing. And if you approximate it like this, so delta P we have already known. You can write this as basically 1 by R del S del X. I request all of you to do not go by the rigorous mathematical things. So, I mean, you can just write it by like this. Okay. So, del P del X you can write by this thing. And for del P del Y, there is another catch, which is that del P del Y, there is a component of this rho gy. Okay. So, you cannot directly write 1 by R del S by del X. You have to consider the rho g first, and as it is downwards, I am considering minus. You can see the convention. Upward is plus. So this is minus rho g, and plus similarly 1 by R, where R is the radius of curvature. This will be del S by del Y. Okay. I hope you get this. I mean, why I did this. So this is delta P, and we have S here. I think it's better to write a delta here. So this would make more sense actually. So this is delta P is equal to delta S by R, and we approximate del P by del X by delta P by delta X. Okay, and which gives our 1 by R, where R is the radius of curvature, into del S by del X. So this is given. We have derived del P and del P del X and del P del Y for our equation. And now we can just directly put in this into our previous equation, and we'll get like 1 by R del S del X times dx, and plus 1 by R del S del Y minus our rho g, rho g times dy. This would be equal to 0. Okay. So yeah, so this is 0, and we will just go on, and you will eventually end up with 1 by R del S del X times dx plus del S del Y dy. This will be equal to nothing but rho g dy. And if you notice, this del S del X into dx plus del S del Y into dy, this is nothing but ds. Okay, so I mean the differential surface tension on an element. So this is nothing but ds by R, where R is the radius of curvature, and this is rho g dy. Okay, and at y equal to 0, I hope you know that surface tension is 0. So if you integrate from 0 to s on both sides, you will basically end up with S by R is equal to rho gy. Okay, which gives 1 by R is equal to rho g by S into Y. Okay, now I hope you know that if the radius of curvature is R, then this term is your basically d2y divided by dx2, this whole divided by 1 plus dy dx whole square to the power 3 by 2. Okay, and now here we were given that this angle theta was very small, as you can see in the figure 2. So we will consider that, and as theta is very small, dy dx, which is almost equal to tan theta or theta, whatever you say, this is much less than 1. Okay, this is given in the question, if you remember. So I mean, so 1 by R, you can approximately say 1 by R is approximately d2y by dx2 And hence you can directly say from here that we get our final answer, which is d2y divided by dx2 is nothing but rho g is times y. Okay, so one key takeaway from this method is that you do not, this method is pretty much more mathematical, as you could see that it involved partial derivatives and all the things like that. We did not do any force balance. If you cannot do any force balance, you can go by this method. I understand that it may have been a little complex for you, as probably you are not very much familiar with partial derivatives and these things. But as you can see, the solution is very short. Okay, so I mean, these things I have just written just for your concept. If you do force balance, it will take pretty much while, and for writing the force balance equation for you, it will also take some time. So if you just do the mathematics here by the approximation and these things, so it will be I mean, time saving for you. Okay, so you can go by this approach. And one more key takeaway is that you do not get the dy dx value from here. Like in the previous approach, probably as much as I remember, if you did force balance, you will get probably dy dx is equal to root rho g by s into y. Something like this came, as much as I remember. But in this approach, you do not get that value. Okay, so if this is required, I think force balance is the best thing to do. But probably you can do some mathematical, what do you say? Some mathematical manipulations and probably get this too from this equation. So what was the key takeaway from our this problem? So from this problem, you may learn that for a surface, for a fluid surface, let me just write it down here. For a fluid surface, any fluid surface, okay, however it is. So for a fluid surface, dp is equal to 0. Okay, and if dp is equal to 0, that means pressure may vary in x, y, z any directions. So you may just write that del p del x dx plus del p del y dy plus del p del z dz is equal to 0. Okay, so you can write this. So, and if you can find del p del x, del p del y and del p del z, so it becomes very much easier. And this method, I mean, it can also be applied to the standard problem of yours. Like let's suppose, so this question is done. I am just discussing some corollary or something. I mean, you may say anything. So let's consider a jar like this. There is a fluid here, I mean, and it is being rotated at some omega like this, and this is the fluid here, and this is the surface. Okay, so probably all of you have done this problem, and I mean, this problem can be solved in actually 2 lines from this equation. How? Let me show you. Just take this as y and x. This is very important. I mean, which direction you are ignoring and which 2 are you taking. For a 3D problem, del p del z will also be there, but probably 3D is out of the scope of JEE Advanced or exams like that at your level. So just let me write del p del y here. So del p del y, this will be nothing but minus rho g, like the previous problem, as there is no other component of except the pressure in the y direction. And for this omega, you will get a del p del x equal to rho omega square r. Omega square r is your centripetal acceleration, and r is nothing but this. So actually the thing is, this problem you can, it's better to solve in cylindrical coordinates. So you can just, yeah. So like this is the equation in Cartesian coordinates. You can also do this in cylindrical coordinates. Will be del p by del r dr plus del p by del theta d theta plus del p by del z dz. This is equal to 0. This is cylindrical polar coordinate. I hope you know, or you might, even if you do not know, it's fine. So our r is like that outward, and this direction is our z, and theta is like that. So theta is like the direction of how do I, like this is the theta, okay, and this is z. So in this, if we use the cylindrical coordinates, we will just get del p del z is equal to minus rho g instead of del p del y, and del p del r, this will be is equal to rho omega square r, where and if you mess this up, if you forgot from where did it come, so let me just take you back to the first first thing that we wrote on this page. So just remember this, okay? The pressure gradient is equal to rho times the body force on unit mass of the fluid. So so x, dimension of x is basically that of acceleration. Okay, so we have considered acceleration multiplied by rho. So this is the thing here, and after this del p del theta term is 0, so you you can basically write here rho omega square r. This is in this is multiplied by dr minus rho g dz. This is 0. Now you just integrate, you will get r square. The limit will be from 0 to r, and at z equal to 0, r is also the a of parabola, the radius. What do you say? Let me go to the figure. Yeah, so z is from here. So at z equal to 0, r is also equal to 0. As you can see, at this point, r increases from here to here. So at this point, r is also equal to 0. So you can just integrate from 0 to r, and this side from there will be rho here, and this side from 0 to z. So rho and rho will get cancelled out, and you finally get omega square r square is equal to 2zz. Okay, so this is nothing but the equation of this parabola. This surface is given by that equation. Okay, so I hope you learned that, and one easier problem you can solve, which I will not solve in this video, but I will just give it to you. And this problem you can solve in just Cartesian coordinates. And see, the key takeaway from these type of problems, this method, is that you do not need force balance here. Okay, so at a surface you just need to write that the variation of pressure is equal to 0, and then you write dp in terms of the partial derivatives, and then just compute del p del x, del p del y, these terms, and then just solve the equation, integrate, or whatever you do. You can just obtain dy dx or d2y dx2, things like that, and also the equation of the surface of the fluid, and also all the things. So this is a very common problem which I am here. So the thing is that this surface, we have a g under, as we always have. So you can just take y and x here. So this is dragged at an acceleration in this side. So if the surface is here, you probably have to drag this. Just give me a second. Yeah, this would be the direction of acceleration. So it is being dragged here. So I think you know that tan theta is given by a by g, and for your practice you can just derive tan theta equal to a by g by this method. Okay, and yeah, that's pretty much it. This is for your practice only. This is the easiest version of this kind of problems. So yeah, that's pretty much it. And just you may get yourself comfortable to this method, as it just involves some mathematical manipulations. No force balance is required and nothing else is required. Just you have to remember one thing, that at this surface the variation of pressure is zero, considering all the directions. So you have to consider del P del X, del P del Y, and del P del Z, all the three directions, and some a term of it will be zero, and the other two you will have to compute like I computed in this problem and the previous one also. The problem asked in NEET was actually quite harder than the parabola surface one. This was quite harder than the next problem I solved. So, I mean, yeah, this is kind of the questions we get asked in semesters of fluid mechanics, semester exams. So, this is part of fluid statics, which is taught in third semester of mechanical engineering. So, we also did this at IIT Kharagpur. So, I mean, this is kind of similar to that. So, okay. I hope you learned the method, and I hope you will consider using this method in different. I hope you have understood the thing, because it may have been a little complex if you are not familiar with partial derivatives and things like that. But it is very, if you get used to it, it is very convenient for you. Suppose that there is a problem in which you cannot do the force balance, so this method becomes very much convenient. So yeah, that's the reason I did this video here, to give you this method, because on YouTube you will have pretty many methods, but this method, I think this applies to all of the problems that you may encounter, and this is a very generic method. This method will apply to any of the problems like this, in which you have a fluid surface and you have to solve for some dy dx, d2y dx2, or even the equation of the surface. Okay, so yeah, that's pretty much it. I hope you enjoyed the video, and if possible, get comfortable with this method, and it may help. Even if it doesn't help in JEE, it will help further if you pursue engineering, especially mechanical engineering and fluid mechanics. So that's it for today. I hope you enjoyed the video, and see you in the next video.